let's get started now. So what I'm going to do today is to give all of you a quick overview of the syllabus for this class, and then we'll start with the introduction to distributed systems. Okay, so first of all, welcome to 677. I'm the instructor. My name is Prashant Shenoy, and we have a large staff of TAs and graders who are going to help me run this class. We'll introduce some of them as well. Okay? So first of all, you need to know that most of what I will be teaching here, labs that we are going to hand out, all of those will have links posted to the course website. Okay? And the links will take you to wherever you need to go to actually complete the assignment. So that's an important resource for all of you. You need to make sure you keep up with the class and know what is coming, and make sure you turn things on time and whatnot. Okay? The syllabus that I'm going to describe today is also posted on the course website. Alright? The class has 3 sections. Okay, so this is the in-class or the classroom section. There are 2 other sections of this class. Both are online, and they are going to follow along with video lectures, and all of you are actually going to follow along in person. Okay? But as far as the course is concerned, all sections are going to do exactly the same work. Okay? Same homework, same lab, same exams. Everything is the same. The grading policy is the same. The only difference is this lecture is in person live, and those lectures are recorded for the other sections. Okay? All right. So course staff, there are 5 TAs. You will get to know them at some point or the other over the course of the semester. Okay, so they will hold office hours. I'm going to post them either today or tomorrow, so that you know what the office hours looks like. My office hours are going to be after class on Wednesdays. Okay, in my office, which is on this floor, room 333. Okay, our plan is to have, because we have a number of TAs, our plan is to have 1 office hours per day, Monday through Friday. So if you need help anytime during the semester, there's always somebody available to help you on all normal working days. Okay? And we'll post that as well. And there are a number of other grading assistants, but you don't need to worry about those for the most part. Okay. So textbook, as far as the course is concerned, there's no textbook. Okay, the textbooks that are out there are really out of date, so I didn't really feel like we need a textbook. There are free copies of the Tannenbaum text, which we used to use many years ago. Okay? So you don't need to buy that, because the authors actually make them available for free download. So you just have to go to their website and just get a PDF, and then you can use that as a reference. It's not a textbook, but it has some good material. So there are links to do that on the course material section of the web page. Okay, so I put a link, you just have to go there and download it. They have a new version for 2023, but it is more or less the same as the previous versions. So get the 2nd edition and get the 4th edition. Those are the 2 more important ones for the class. Okay? And I put up all the notes from last semester also on the course website. There are about 200 pages of notes. Okay? That's really the resource that you should care about, because it has all the material from what I actually teach in the class. Okay? So between course notes and these suggested books, I think we should have plenty of material. I'll also have pointers to papers that you need to read as we go along. All right? Any questions so far? So course outline, these are the topics we are going to cover in this class, not necessarily in this order, okay, but let me go through them. So today we are going to do an introduction. Okay, next time we'll talk about distributed systems architectures, okay, all kinds of architectures that you have to think about when you design distributed systems. Then we'll talk about inter-process communications, RPCs, RMIs, some of you may know about them, but we'll go through them, understand how you can design communication between components of a distributed systems. Then we'll get to processes, scheduling, virtualization, topics of that sort. I will do a little bit of naming and location management, not a whole lot this time around.
The audio is not working on you, so maybe you have to turn your mic off or something.
Okay, so then the rest of the class is going to have more advanced topics, including canonical problems in distributed systems, which include mutual exclusion, leader election, clock synchronization, and so on. Okay, then we'll talk about replication, caching, consistency, and distributed file systems, fault tolerance, security, middleware. Okay, that's a long list of topics, but what we have done over the past few years is we have added more relevant topics to that. Those are classical topics in distributed systems. But over the course of the last few years, we added topics like web computing, cloud computing, edge computing, sustainability, big data, multimedia, Internet of Things, and so on. Okay? So those will be interspersed in this list. Okay? So it's not like we do them all at the end. So we'll see that we do them in some order as we go through these various topics. Right? Okay. So that's the outline. As far as the course grading is concerned, there are 3 exams and 3 labs. That's going to be most of your grade. Okay? So 2 midterms and a final, which is 50% of the grade, 3 programming labs, that's 45%. There are some small assignments, which are going to be 4%. The assignments will be some combination of lablets. Lablets are not real labs, they are really tutorials where you just learn about a topic that you're going to use to actually program a lab. Okay, so it's background for a lab, so there are small homeworks that you have to do and some problems. Okay, and then 1% for class participation, participating on Piazza and so on. Okay. Any questions on this so far? Okay. As far as the course prerequisites are concerned, there are 2. Okay, first is that the assumption is you have taken an undergraduate course in operating systems or have familiarity with concepts in operating systems that are taught at an undergraduate level. Okay? Now, we don't enforce this requirement, but it is an assumption that we are going to make as you cover all of these topics. Okay? If you haven't taken that class, there are plenty of free textbooks that are available. I can point you to some. You can go and read them up on your own. Okay? But if you have any concerns about that requirement, come see me after class or during office hours. Okay? The other important requirement is, of course, you need to have good programming skills, because nearly half the grade is going to depend on labs that you're going to program. Okay? And you can do them in Python or Java, the programming language. There's some flexibility in what you are going to use. Right? Okay. So we are going to use Piazza for online discussions. If you have any questions, you're better off actually posting, making a post on Piazza or sending a private post. Try not to email us unless it's a real emergency, because this is a very large class. There are around 200 students. So if we have lots of emails, we may lose track of them. If you post things on Piazza, somebody will answer them and we can keep track of what we have said and whatnot. Okay? So that's where we are going to have discussion. That's where you can ask questions of me or the TAs. Okay? We are going to use GitHub Classroom for the labs, and we are going to use Gradescope for turning in assignments, and that's how we'll return your exams as well. Right? Tools that you should all be familiar with anyway. Okay? I think we have enrolled most of you in all of these 3 things. So you should have gotten email saying you are on Piazza, Gradescope, and GitHub. If you are not, just let us know, and then we'll make sure that you are on it. All right? YouTube channel is where all the recordings are going to go. Looks like we lost the first 5 minutes of today's class because the mic doesn't work for some reason, but we'll fix that later on. Okay? But most of the classes, so long as Zoom works, we will record and put up on the YouTube channel for the class. All right? And Moodle is going to be used mostly as a grade book. We don't really use it to do anything. Everything else is on these other tools, but all your grades are going to be recorded on Moodle. So that's where you need to go look at all of your grades. Any questions on this so far? Okay. So I urge you to go read that syllabus. It has lots of details. Make sure you understand all the things that are said in it. Okay? And there are a few policies. There are maybe half a dozen policies on the course syllabus. Go read them. There are 2 or 3 I want to mention. Class participation policy. Okay? The class is going to be more enjoyable if you ask questions. Okay? raise your hand, ask questions. At some point, we'll also enable questions from the online students. Okay, so that's basically a good way for you to learn about topics. If anything is not clear, you should just ask a question. Okay? Because there may be others who don't understand what you don't understand as well. Okay? The other thing we need is a scribe for every class. The job of the scribe is to take notes about what the lecture is about and then make it available to the rest of the class. Okay? So later today we will send out a sign-up sheet. So we need 25 or so volunteers. Okay, so not everybody needs to sign up, but if you think you are interested in helping with some lecture, you can sign up for that date and you will be the scribe for that date. Okay? And then we'll send you instruction on how you're supposed to write the notes up and send it back to us. Okay? And we'll make those available to the rest of the class, so your help would be appreciated by all of your fellow students. Okay? Masking policy is the same as the UMass masking policies. Masks are always welcome. Okay, so please respect the choices that everyone is making in this class. Okay? The last policy I want to remind everyone is we have a device policy, which is not to use devices in class. Okay? So if you use a laptop, like to use a laptop, you should not use that in this class, please. Okay? Because I think that most of the time people just don't pay attention if you have a laptop open in front of you or a tablet or anything like that. Okay? Phone should of course be turned off or put in silent mode. Okay? This is going to ensure that we will have a better experience in this class. So for those of you who brought a laptop or an iPad, please shut it down. Okay? For the class, I will post the lecture slides, the recordings. You are welcome to print the slides before class and bring them to take notes. Okay? So that's how we are going to run the class. Okay, any questions? Okay, so let's start with the actual material for the first lecture, which is distributed systems. Why are they a topic that we should care about, and what are distributed systems? Okay, so first thing to keep in mind is most computing systems that we interact with on a day-to-day basis are distributed in some shape or form. Okay, whether it's with the web, the Google search engine, cloud computing, e-commerce website, Amazon, or any of your favorite retailers, peer-to-peer file systems. There are systems called SETI at home, which you may or may not be familiar with. We'll talk about that later. Grid computing, modern network computers, all of them are distributed in some shape or form. Okay, so if you really want to understand how computing systems work, okay, in this day and age, you really need to understand how distributed computing systems work, because most computing systems are by and large distributed in nature. Okay? So that's the first reason we want to understand how these real world systems work. And what this class is about is basic design principles that help you understand how you should build a distributed system should you have the opportunity to do so at some point in your career. Okay? So we'll cover these basic principles. As part of the labs, you will understand these principles in depth. And hopefully by the end of this class, you should have an understanding of how these complex systems work, what kinds of trade-offs to make if you want to design one of these, okay, and of course some experience in building them yourself. Okay, so that's really the learning outcomes we are shooting for in this course. Okay? All right. So let's start with a simple definition of what is a distributed system. Okay, so this definition says it's a collection of computing elements, CPUs, that are interconnected together. Okay, so collection of independent computers that are that appear to its users as if they are single large coherent system or a logical system. Okay? It's a very broad definition. Okay? Many kinds of systems that we may or may not think of as a distributed system will meet that definition. Okay? So parallel machines would meet that definition, network machines would meet that definition, your smart TV might meet that definition, your phone might meet that definition if it's interacting with other elements and so on. Okay? So we'll keep that definition broad because, as I said, lots of computing systems are distributed in nature. So we really want to understand how all kinds of these devices work. Not just how cloud computing works, but you want to understand how mobile computing might work or how IoT devices work. Because all of them will fall under this definition. Okay? So that's our working definition for the rest of this course. Okay? So keep that in mind, okay, what we mean when we say a distributed system. Okay. So why would we want to make systems distributed? Why not build centralized system? Okay, what do we get by making a system distributed? Okay? There are some advantages, and of course there are always disadvantages when you have any type of computing system. So let's look at both. Okay? So first thing when you make a system distributed is that it enables sharing of resources. Okay? Because one computer can now communicate with another one over a network. Resources on the second computer can be accessed over a network. Okay? So this could be files that you store in the cloud, okay, on Dropbox or OneDrive or Google Drive. Okay? So you're accessing now storage resources that are not on your local machine, they are somewhere else on some other machine. Okay? So that is possible because now machines can communicate, okay, and share resources. Okay? Another reason is economics. Okay? Building systems in a distributed manner gives better price to performance advantages that centralized systems simply will not. Okay? You can make large clusters with the price of this cluster to build this cluster and compare it to a price of a large supercomputer. You will see that some of these distributed systems provide an attractive price to performance ratio. So from an economic standpoint, this is an advantageous way to build distributed or make systems distributed. Okay? Now you also get reliability and scalability benefits, and we'll get into some of this in more detail later on. But very briefly, what we mean by reliability, since there are multiple machines that are part of a distributed system, if one or some small number of them go down, the rest of your system can continue to function. Okay? So long as those other machines can take over the task that the failed machines are performing. Okay? So failure of some number of machines need not make the entire system stop. Okay? That's a reliability advantage. There's a scalability advantage, which essentially says that actually building systems in this manner, where you have smaller machines that are all, I shouldn't say small, there are machines that are all interconnected, actually gives you good scalability benefit if you build your applications the right way. Okay? You have to make sure that applications are designed to scale in that manner. If so, you are going to get those benefits as well. Okay? And there's potential for incremental growth. Your system can grow over time. Because it comprises of independent machines, you can add more machines to a system that will increase its capacity, will increase its performance, enable it to give higher throughput to the users. Okay? So all of those are advantages. Okay? So now what are some downsides of making a system distributed? So the first is it makes your application more complicated. Okay? Your application is no longer one process that is running on one machine. It's a collection of processes that are running on multiple machines that are all communicating with one another. So this means now you have to understand how to design your application, what components to put on each machine, how they communicate, and so on. Okay? So application design, okay, is more complex. Okay? What that also means is tools that you will use to design your application also have to be more complex. They have to be aware of the fact that you're designing a distributed system or an application. So your programming languages, operating systems, middleware systems, they all have to be aware of the fact that this is a distributed application. Okay? As opposed to just a single machine running an OS where it's not actually communicating with any other machines. Okay? Network connectivity is essential in your distributed system, because if your network goes down, okay, then I think your application is not going to function, because it requires the ability to communicate with other entities on your network. Okay? That's not so in a centralized system. You can just continue to work on your editor if your network connectivity fails, because it's all local to your machine. Right? That won't be the case if you have a distributed application. Okay? And security and privacy considerations are also important. Okay? Once you start putting things on a network, they are vulnerable to hackers. Okay? Somebody can break into your machine and steal your data. Okay? Okay? Your privacy may be compromised. Okay? If your machine is not networked, that will not happen. because you cannot actually access a machine that's not on a network. Okay? So those are some disadvantages to keep in mind. Okay? By and large, okay, we would believe that our advantages that I've listed here are going to outweigh the disadvantages. Otherwise, there wouldn't be a reason to do this, okay, or build systems in this way. Okay. So let me talk a little bit about transparency in distributed systems. So what this means is when you're going to design your system, you're going to have to make a number of choices. Okay? What is it that your users will see? What is it that you will hide from your users? Okay? And depending on what choices you make, okay, your system might look very different to its users. Okay? And the general design principle is you don't want to expose needless complexity to your user. You want to take care of this complexity in the system and expose simpler abstractions to your users so it's easy for them to actually access and use your system. Okay? And what you hide and what you show or expose rather to your users actually is captured by this term transparency. Transparency means making or exposing something to your user, okay? Or not. Okay? So let's take an example. Okay? And let's take, we're not going to go through all of those things, but let's take one example here, which is replication, or replication transparency. Okay? So replication transparency essentially means that you are hiding the fact that some application or resource is replicated from the user. Okay? User can access that resource without knowing that it's replicated. Okay? So it's best understood with an example. Okay? Let's take the Google search engine. Okay? What's the interface that you use to interact with the search engine?
Search bar.
Okay, the search bar. Okay? Very simple interface.
Yes.
Okay? You just type some words and hit search. Okay? Google doesn't tell you that that search query is being processed by hundreds of or thousands of machines in the back end. All of that is hidden from the user. You don't say send this query to the 510th machine that's sitting in the Google cluster. They could have exposed that, then your life would be much harder in how you interact with your search engine, okay? Which is a highly complex and highly replicated distributed system. Okay? So this is an example of replication transparency where all of that complexity is completely hidden from the user. The user is a very simple abstraction. You don't even have to think. You just type some words and you hit search, and then you don't actually need to know what is happening before the results come back to you. Okay? So that's an example of a good design. There's many such complexities that are inherent when you design your system can either be exposed or be hidden. Okay? As a designer, you have to make the choice. It's not always good to hide everything, because when you hide things, then if the user needs the ability to actually take flexibility of some attribute, you are hiding it from the user. Okay? So you have to decide, and the answer is going to depend on what it is that you are building, okay? Who your users are, how they interact with the system, what you want to expose, what you want to hide. Okay? But these are some dimensions that you can decide in terms of what attributes or properties of the system on what you expose and what you don't expose. Okay? So replication transparency says you don't expose the fact that the system uses replication. Okay? Location transparency says you don't expose the location of where a resource is from the user. Okay? URLs are a good example of that. Okay? You just have a name, which could be umass.edu. It doesn't tell you anything about where the server is. The location is not known to you. You just have an address. Okay? Typically, when you have an address, a physical address, it actually gives you the location of whatever you're trying to look up. In a web address, that location is hidden. Okay? It just tells you the name of the site, but not the location of the site. That's an example of location transparency, and so on. Okay? We won't go into all of this, but we will get to most of this as we go through the course. Okay? Any questions here? Yes, please.
So in a replication, like when we search on Google, so it shows how many particular searches it has taken to find that particular query we have inserted in it. So it's like replicated in some sense, like finding the proper sentence query we have.
Yes, the question, if your question is when you search for something on Google, it gives you some The response tells you a little bit about how much time it took, and some attributes of how the query was processed. Is that replication transparent? Is that what you're asking?
Yeah.
So I think it's just the fact that you are presented with some results on how long it took for the query, how many hits are actually being shown. That doesn't mean that you know what the degree of replication is, how many servers are there, and so on. So I think it is still replication transparent, okay, because you can't directly interact with a particular replica. So all of that is hidden from you as a user. Okay. Anything else? Okay. So the next attribute we want to talk about is what we will call open distributed systems. Okay. I think the one thing to keep in mind is there's a difference between open systems and open source systems. Okay, open source systems means the source code for the system is available. Okay, you can download the source code and you can use it, modify it, and so on. Open distributed system just say that the interfaces are well described and open, that you can use those interfaces to build your own applications and interact with it. Okay? So many systems now expose APIs. Okay? Those are a set of functions that you can use to interact with that service, build your own application. Okay? One example could be Google Maps. Okay? Google Maps actually publishes its interface. Okay? You can use that interface to embed maps into your own application. That's an example of an open distributed system. The interface is known, okay? It allows you to interact with that service via specified interfaces. Okay? The benefits of doing this is it makes the system more interoperable because other entities know how to interact with that system. Okay, it's also more portable because you can write other clients that talk to it and so on. And it could be extensible. You can use those interfaces, write your own libraries, and expose new interfaces if you so wish. Okay. So there are many advantages in building systems that are open, where you publish your interface and there's a well-described way by which you interact with the system. Okay? As opposed to closed systems where the interfaces are not published. Okay? You cannot actually write your own application to interact with it. You have to go with whatever the developer or the vendor has provided to you. Okay? So that's an important attribute of distributed system. By and large, lots of the services you see on the web tend to be open. They have interfaces that you can actually use as a developer and interact with that system, write your own clients, write your own functionality, and so on. Okay. Now, the other thing we want to discuss as far as distributed system is concerned is, I mentioned that one of the advantage was scalability. As a replication, scalability, and so on. So let's delve into that in a little more detail. What does that actually mean? Yeah. So the best way to think about this is to compare a centralized system with a distributed one and see how the same application will change as you go from centralized to distributed. Okay? So there are many ways to think about how a system is centralized. Okay? You can have a centralized service, which means there is a single server that is serving all users. You may have a web server or a game server that runs on one machine. Okay? That's a centralized service. Okay? You might have centralized data, okay? Which means that all the data used by the application resides on one machine or on one database. Okay? And you could have centralized algorithms which say that all the algorithmic concepts that you use to write your application, they're all centralized. Okay, they have to run on one machine, on one process. Okay, as opposed to decentralized, where the algorithm itself, as pieces, they run on different machines. Okay, so centralization can take many forms. The service could be centralized, data could be centralized, or algorithms could be centralized. Okay, and the point we want to make is if you do this, okay, in some cases, that might be the right way to build your application. It's not that every application should be distributed. That's not really what you should be taking away from this discussion. But what you should think about is, as the number of users grows, as the number of requests that are coming into the system grow, okay, if you design your application in a centralized fashion, eventually you will hit a bottleneck. The bottleneck will prevent your system from serving a larger number of users. Okay? That should be apparent if you take centralized services. Excuse me. So if you have a web server, okay, and let's say you write a blog article that becomes very popular, lots of users come to your website. Okay? Your website might actually get overloaded and simply crash. Okay? Because it cannot scale beyond a certain capacity. It's running on one machine. Okay? Its capacity is limited to what the number of users that that one machine can support. Okay? That's an example of a centralized service. Same with centralized data. Okay? If you put a lot of data, I shouldn't say a lot of data, but very popular data on a single machine, okay, in a single database or something like that, and lots of queries come in, the database may get overloaded. Okay? And it cannot then serve more users if it's already running at capacity or is saturated. Okay? And it's the same is true of algorithms, where you might have bottlenecks if you essentially try to scale your system. Okay? So the main takeaway here is that all centralized techniques will have a point where you will hit a bottleneck. You cannot scale the system beyond that point. So if you want to do scale beyond that point, you only have some options. Okay? You can either put all of that centralized code data on a bigger machine. Okay? You just buy a bigger machine, more disk, more memory, more processing, then capacity goes up. Okay? To the extent that that machine can support more users. So that's one option. The other option is you make it distributed. So either buy a bigger machine or you make it distributed where it runs on more than one machine, and hence it has more capacity to serve users in one. Okay? So that's essentially the scalability argument of why we want to make our systems distributed. Okay? All right. So how do you do scaling? Yes, there's a question in the back.
Can you elaborate on the centralized algorithms? Give an example probably.
So, example of a centralized algorithm. So I think there is an example here, but I'm not sure that's the right one, but I'm going to use that one. Okay, so if you want to do routing in a network, okay, routing just says if a packet wants to go from machine A to machine B, what path should it take? Okay. If you do a centralized routing, that means that there's a central entity that knows the entire topology of the network. If you say this is a packet on this node, it needs to go here, it's going to make a path for you based on its knowledge of topology. Okay? That's a centralized method. Okay? Now that method is simply not going to scale as your network goes bigger and bigger. Okay? If you want to do routing in the internet, there's no centralized entity that can first of all know the topology of the entire network. It's just too large. And even if you knew it, okay, just trying to route packets at large scale is simply not going to scale.
But this is still the same algorithm running in the different machine, right? But what I'm confused about with that example is the data or the topology that is being used for routing is what's different, but the algorithm is essentially the same.
So that's a different question. So the question now is, if you want to make a centralized algorithm distributed, are you going to run the same code on multiple machines? Okay? That is replication. That is not necessarily distributed algorithm. A distributed algorithm would mean that you actually change the way that algorithm itself works. Okay? So you can replicate. That is one way to scale. Okay? In fact, what you would do here, if you run out of capacity on one server, you will simply take that application, run it on a second machine. Okay? And somehow you will distribute the request. That's what you would do for a website. Okay? You have the same code on multiple machines, and there's the same logic and everything, and you're just distributing your request. That's replication, not decentralization. Okay? So centralized algorithm here means that everything is running on one machine, but you want to scale it up, you want to inherently make it distributed. You will have to come up with a different way to actually implement that functionality. Okay? Yes?
Should we call MapReduce as a distributed algorithm? Like,
Can you repeat
will we
that?
call MapReduce as a distributed algorithm?
Okay. Question is, will we call MapReduce as a distributed algorithm? We would call MapReduce as distributed. We'll get to MapReduce at the end of the class. Maybe you learned it in another class. That's okay. Here we look at it from a distributed standpoint. But yes, since you are going to run that job on multiple machines or multiple processes that run on one machine, it is distributed. Yes.
If the algorithm is set up such that in like one location there's like a leader algorithm and then there's a bunch of worker algorithms and there's a discrepancy and they all report back to that, is that still distributed?
Okay. So your question is, if you have a system where there is one node which we'll call the leader, and there are lots of worker nodes that are doing some work and they're reporting back to the leader. Is that distributed? That's your question. So that is an example of a distributed algorithm. It's a very popular architecture. Okay. In the old days, this was called master-slave architecture. Master and slave, don't use that terminology anymore. So they are called workers and leaders and workers and coordinators and so on. But yes, that architecture is definitely a distributed one. And we'll come to that next time.
Oh.
Okay. Anything else? All right. Okay, so as far as scaling is concerned, what can you do to scale? Okay, there are 4 basic properties. At this point in the class, I think probably you won't understand the subtle details of what is here. But as we actually make progress and learn about more topics, you will get a better appreciation of why these properties are needed to scale. Okay? First property says that if you want to scale your system, okay, or you want to make your algorithm distributed, you should not have one machine that stores complete state. Okay? All of the information needed for your application to work should not be on one machine. State is essentially information that you need for analyze the state. Okay? That is going to create a scalability problem. Okay? You should not require global knowledge of the system to make decisions. Okay? If every entity in the system needs to know about every other entity in order for it to decide where to send a request, where to send this packet, you are going to lose that battle very quickly. Okay? You are not going to scale because as the system grows, the amount of information you have to keep track of itself will keep growing. Right? So to the extent possible, you want to make decisions based on local information, not global information. Local information means I can make decisions locally without having to talk to everything else on the network. Okay? That's going to scale better. Or if I have to ask all these other machines for some information to make some decision, that will increase my overhead. Okay? So make decisions based on local information. Do not maintain state on one machine. Okay? Ensure that a single failure is not going to bring down the entire system. Okay? This is called a single point of failure. Okay? Often happens. Okay? All kinds of failures that you read about essentially are because the system somewhere has one point of failure. You might replicate your code, you might replicate your data, okay? But maybe you do not replicate the switch that's actually communicating with your machine. If the switch dies, your network is gone. Right? So you have a single point of failure, even though you think your application, you wrote the code well, you distributed your data, but somewhere there is a single point of failure lurking that's going to take your system. Okay? Excuse me. So to the extent possible, okay, you should not have systems where one failure is going to take the entire system. Okay? You should use replication so that failure of any one component allows other components to take over that task. Okay? That will allow you to build a better system. Okay? And the last property is what is called a global clock. Okay? So global clock essentially means you should not assume that all of your machines are perfectly synchronized in terms of their time and clock. Okay? Because as we will see when we get to a later topic, a lot of decisions that you make in a distributed system are based on timestamps of when certain events happen, reasoning about okay, which event happened first and what decisions to make based on order of events and so on. Okay? A lot of these timestamps might use real clock values on machines, okay? But machines can never be perfectly synchronized. So all synchronization algorithms are going to have errors in it. Okay? So you will always have some chance that something might go wrong if there are two events that are very close to one another and your clocks are not perfectly synchronized. Okay? So a global clock essentially means perfect synchronization. Okay? And it's actually impossible to achieve. But if you assume that is what is the case, then there may be some chance that something might go wrong every once in a while. Okay? So those are all properties that you should ensure to have a scalable system. Yes?
Is OSPF algorithm considered to be a good decentralized algorithm?
Okay, so this is a good question, but wrong class. So the question is OSPF, which is a network routing algorithm, is it a good decentralized algorithm? Short answer is OSPF is widely used in network routing. Okay, so all routing algorithms are decentralized. There is in the internet there is very little centralized routing that goes on. whether you use OSPF, shortest path, which is a shortest path technique, it's all decentralized. Okay? Yes.
If a machine that is in complete state takes a decision without the global information, just on the local information, could it happen that takes such a decision that makes it not compatible with the other machines in the system?
Okay, that's a good question. The question is, if you are going to make a decision based on local information without asking for other nodes to provide some information or without requiring global information, can you make incorrect decisions? Okay? The answer is actually yes, you can make incorrect decision. Simple example is, let's say you want to do load balancing. Okay? You have 3 servers, let's say in an application. Whenever a new request comes in, you want to send it to the least loaded of the 3 servers so that it gets the best service. Okay? So question is, when a request comes in, how do you know which machine has the least load? Okay? If you ask all 3 machines for their load, that is global information. You know, every time a request comes, I ask all 3 machines, okay? And then I basically pick the one with the least load. That's a fine algorithm, but it's requiring you to know complete information, load information about all machines in this application. Okay? Now you could have local, you could make local decision. You might say, okay, I'm going to just do round robin. Say request 1 goes here, request 2 goes here, request 3 goes here. Maybe that's a fair way to distribute requests. I don't need to know anything about load because I'm just doing round robin. So every machine is getting a third of the requests. Okay? Maybe fine. Okay? But what if requests are heterogeneous? Some requests take longer, some requests take shorter. Okay? Some machines might end up with long requests and they may have higher load, and other machines got the short request, they have lower load. You may make a wrong decision if you do round robin. Round robin may not give you least loaded. Okay? A simple example. And there are all kinds of reasons why when you make decisions based on local information, it may sometimes not be the right decision. Okay? But you have lower overhead to make that decision. Okay? Question there?
So you mentioned that there is no global clock in a distributed system. So how does synchronization happen then? Like in case there was a trigger event, like some machine was supposed to interact with another one, but there is no time stamping, or there is no synchronization, then how do you work with that?
Okay, so that's a question we will actually defer. I'm going to repeat the question, but we are going to defer that to a later class. The question is, if you don't assume a local, global clock, excuse me, then how is synchronization going to occur? You don't have timestamps and all. So we'll get to this when we talk about logical clocks. We'll see that there are ways to synchronize systems without using real clocks. Okay? It's not going to solve all our problems. Real clocks are still very useful, and they're widely used in a variety of distributed systems. Right? This is an ideal property. It doesn't mean that if you use it, something bad is going to happen. It just say that should be the ideal. Use as little of it as possible. But there are ways to not use it at all. Okay? So it's not possible for me to explain now how to do it. We have to build some background before we get there. We will get there in maybe 12 or 13 classes. Anything else? Okay. So those are the 4 properties. There are ways to do this using asynchronous communication. We will study that in a little bit. There's ways to do this using distribution, caching, and replication, which we'll also get to. Okay? So these will allow us to actually make a system adhere to those properties to the extent possible. Okay? So with that, very quick, though, that was the introduction. Module 2, we just did that. I'm going to give you a little bit of a history. Okay? And then we will wrap it up. We'll talk a little bit about operating systems, and then we'll wrap it up for the day. Okay? So there's a little bit of history here as to how distributed systems arose, what kinds of models are out there, and so on. So in the early days, we had what was called a mini computer model. Okay? There was one machine, users had terminals that they used to connect to that machine, and they just worked on those terminals. And these machines have very slow networks that they could use to talk to other machines. Okay? Those were very early distributed systems. Now as machines got more powerful, we went to a workstation model, where every user had a desktop, powerful desktop, that had a local area network. Okay? So you could essentially work on your machine, you could access resources on another machine, you could send jobs to another machine, and so on. Okay? So that's an evolution from a mini computer to a workstation model. The workstation model then evolved to a client-server model. Okay? There were more powerful machines called servers, and you had clients or workstation. Okay? If you wanted to do heavy-duty work, you sent it off to a server. Or the server provided services that clients could access. Okay? So that model is still prevalent today. It's widely used. Okay? But that's basically what came out of what was a workstation model. Okay? Then we had a processor pool model where the servers had lots of processors. You could then assign work to specific processors. Okay? That basically evolved into a cluster computing model, where the processors were machines, okay, or processors were CPUs on independent machine that were part of a cluster and so on. Okay? So this evolution has continued. Okay? It's not stopped, it's continuing to evolve. So your cluster computing systems that became large clusters became data center computing. Okay? Then you had grid computing where data centers were federated so you could talk to one another, so you built even bigger systems. Okay? Then you had cloud computing, okay, and that basically was driven by virtualization and so on. Okay? So that evolution has continued, and now you basically have distributed systems in ways that you don't think of them as distributed, and that's essentially where you are now small nodes, not big systems, but small nodes that communicate with other small nodes, and now you have pervasive computing systems. Okay? So example is your smart TV is a distributed computing system. Okay? Your car is actually a distributed system. It has many microcontrollers. Many cars actually have local area networks where these microcontrollers talk to one another. Most of the modern cars are connected. They actually talk to a cloud. Okay? They can report when an airbag is deployed. All kinds of things can be reported back to a center so somebody can send help. Okay, so it's actually a distributed system. You don't think of an automobile as a distributed system, but its computing base is effectively distributed. Okay? And then you have sensor networks where you have small sensors that are deployed in the environment that communicate with one another. That's distributed. You have all kinds of wearable devices that are distributed. So essentially this has now become a way you actually design your systems. You don't put all of your logic on one machine or one node. You essentially put them on multiple nodes, have a network. And networking is cheap, hardware is cheap, so you can actually build larger network and build systems this way. Okay? So we'll actually track this evolution to some degree in this course. I'm not going to go through every bullet I talked about, but we'll look at some sampling of those and see how you design systems for each of those categories. Okay? Okay, so very quickly we'll go through operating systems and their evolution. So the course does have OS components, not all distributed systems. So we'll look at other kinds of operating systems beyond the one you should already be familiar with, which are uniprocessor operating system. That's what you should have learned in an undergrad OS class if you're taken one. If not, you should read a book and at least get some familiarity with what a uniprocessor machine looks like from an operating system standpoint. Okay? So in this case, the OS is a special program that's going to run on your machine that manages all the resources on your machine. All of the hardware is managed by the OS. Okay? It basically provides an easier to understand abstraction to users. Okay? You as a user can make a file and ask the OS to store it. You don't have to tell it store it at this location or disk or anything like that. It's going to take care of it for you. When you start an application, it becomes a process. You don't have to specify to the OS how much memory to give it, what kinds of resources to allocate. The OS will take care of it for you. So it is essentially a resource manager. It's basically taking that task on, so it's much easier for the users to use their machines. It's providing more logical abstractions of what memory looks like, what a disk looks like, through a file system abstraction and whatnot. Okay? So that's our standard baseline for what an OS is going to look like. Okay? And there are many such operating systems, some you're probably familiar with them. The early ones were monolithic architecture, Microsoft DOS and early Unix, where that entire OS ran as one piece of code on your machine. When you boot your machine, the kernel boots up, the OS kernel boots up. That is a monolithic entity that just runs like one privileged process. Okay? That's how early operating systems were designed. Okay? Now, as you can imagine, that's no good way to write any software. Okay? You just make the software one big blob of code and it just keeps getting bigger and bigger. Okay? You want to make, from a software engineering standpoint, any application you build, whether it's centralized or distributed, has to be modular. It should be easier to change, easier to maintain, and so on. So if you build your operating systems as a monolithic architecture, that quickly doesn't work as your system gets more complex. Okay? So a variety of other architectures have been designed that address some of the shortcomings. Okay? One of which is what is called a microkernel operating system. Okay? As the name microkernel suggests, okay, the OS kernel is a small compact entity. Okay? When you boot up, the microkernel is going to boot up. All of the functionality that you normally associate with an operating system actually run as user applications in user space, and they communicate with one another. Okay? Your memory manager, okay, normally is inside an OS, but here it's going to run as a process. Your file system is going to run as another application process, okay? And so on and so forth. Okay? So your file module, process module, memory module, and applications also run as processes. Okay? Very different way of designing an OS. You pulled out a lot of the functionality and you started running them as user processes. So now let's think about why this is a good way of designing a system or an operating system. What did we get by doing this? Yes?
Replication.
Yeah, what can you elaborate?
Each of the individual modules can be a separate service. So you
Okay.
can-
Each module can be a separate service, that's correct? Yes?
It's easier to maintain things because you don't have one massive code base that is completely interdependent versus having very well structured separate components.
So you have independent services, software engineering benefits. You don't have to actually look at one big piece of code. If you want to modify the file system, you just need to look at this process or module. Okay, that's all you need to modify. There are well-defined interfaces that let modules talk to one another. Saw some more hands up. You had something? Yes.
You can easily add or remove modules.
You can add or remove modules. These modules run as user processes, but yes, you are talking about slightly different architecture, but you are right. You don't have to have all of them running at the same time. Yes.
I don't know, but maybe since these are different modules, there's like an aspect of security between the modules. So there's like more, it's
Okay.
more secure system.
More secure system. Okay? I'll give you after this class a link where you can read a lot more about this, because microkernel designers claim that this is inherently a more secure way of writing an operating system. Their point is, if you have monolithic architecture, if you have one bug inside the OS that you can exploit, you essentially get access to the entire OS, okay, which runs as a privileged process, so you essentially can take over a machine. Okay? Or you can bring the whole machine down. Okay? Here, if you have a bug in your file system, okay, maybe that process crashes. Your files may become unavailable until you restart it, but your OS, the rest of the OS can continue to function. Okay? Because you cannot exploit a bug in the file system to now take over the memory manager and then start looking at memory contents of processes and start stealing it. Okay? So this is essentially an advantage of a microkernel architecture. Okay? And there's a long debate about this. Is it really an advantage, not an advantage? So the link I'm going to post is actually a debate. Actually, it was a flame war more than a debate between Linus Torvalds, who designed Linux, and Andrew Tannenbaum, who wrote the textbook that I was mentioning earlier. And Andrew Tannenbaum was a proponent of this architecture. The Linux started as a monolithic architecture. Now it's more modular, no longer monolithic. So they had a long argument about it. So you should go and read it just for you to understand what they were saying about the pros and cons of this architecture. Okay? But let me ask you what you think might be downsides of this architecture. You talked about some advantages, which are all true. Is there a problem with this architecture that you can see? Yes?
It's more difficult to write code for.
It's more difficult to write code for. No, he said it's much easier to write code
Oh,
for.
okay.
Because you just need to know what that component does to modify.
Okay.
Okay, so you can't say it's easier and difficult at the same time. So only pick one. Yes?
There's a lot of communication that's going to happen and the interfaces need to be well defined. So if someone is changing something in the process module, that change needs to be, like everyone needs to know that the thing is changed. And if the development, as we saw, that software engineering is it's not happening at the same time. So that communication should be so.
So interfaces have to be well defined, that is true. Yeah, without that there will be a problem. Do you have something else you want to add?
In a monolithic kernel, it's assumed to be running in a privileged execution, whereas these are, each module is supposed to be userland, so you have to now handle the proper escalation to a privileged execution for each userland module, and that creates
Okay, so
processor attack.
you're right. That's something more. Yes.
I'm guessing there might be some performance penalty on this architecture, like if it is monolithic. The function call is just multiprocessor pointer. In this case, we might involve some inter-process communication.
Yes, so I think that's definitely a big disadvantage, and what was mentioned here is there is a performance penalty to this architecture. Okay, so first of all, you have to realize that all these components, which are now modules that run as user processes, have to talk to one another because they are performing a task as an operating system at the end. The memory manager to allocate some memory. So they do have to communicate. In a monolithic architecture, all of these components are inside one process. So essentially it's function calls. Right? That's how you write a centralized application. You have objects or you can have function, you just call functions. Okay? What are function calls inside a single process and essentially become inter-process communication across independent processes. Okay? And sending a message is a lot more expensive than making a function call. Okay? So you are going to get a huge performance penalty because there's a lot of communication that is going to go back and forth between these processes to actually fulfill the tasks of an operating system. Okay? The entire job of the microkernel, okay, is to have efficient inter-process communication because that's the heart of everything here. And without that, this system. So this is, in some sense, looks like a distributed system, but it's not because it's running on one machine. But a distributed system will look like this. There will be components there on different machines. Okay? So communication penalty is going to actually cause a performance penalty. Okay? This is by and large why microkernel architecture, even though they are actually more secure, did not really become popular in any commercial operating systems. Okay? They tried. Okay? Windows actually went from a monolithic to a microkernel architecture. Okay? Mac OS actually went from a monolithic to a microkernel architecture. They soon saw that the performance was really slow. Users didn't like it. Okay? Users want their machine to respond when they are working on it. They don't want the machine to really work slowly for them. Okay? So what did they do? Okay. They started taking some of this and put it back inside the kernel. Okay. So Windows NT was actually a microkernel architecture, and the next version of Windows, they started moving things back. Some things are still outside the kernel, but lots of things have gone back in for performance reason, no other reason to do it. And same thing is happening with Mac OS and so on. Okay. So they still have some microkernel flavor, but by and large, they now have more of a monolithic architecture, but to ensure software engineering benefits, the monolithic architecture uses software modules. Okay, so modules are not running as user processes. Their modules are essentially components inside the OS. It's like using an object-oriented framework where your object is essentially your encapsulation of code and data. Except that you're not really using object-oriented architecture. It's just a concept of a module that looks like that. It has code and data. It provides a service to others. Okay? So that's your modular monolithic architecture. So you've gone back and forth. Okay? So that's still ongoing as to what should be inside, what should be outside the OS. Okay? So now let's talk a little bit about distributed operating systems. So what is this? Okay, essentially, you have machines that run uniprocessor operating system. They can run microkernel operating system and so on. So you can now take all of these machines and you can put them on a network. Okay? What you have is a distributed system according to our definition. You can literally take two laptops and put them on a network, and that's your distributed system. It needs at least two machines. Okay? But in this case, your OS has not hiding the presence of multiple machines from you. Okay? you have to actually know that, you know, if I want to access resources on that machine, I should log into that machine, and so on. Okay. Now, if you have what is called a distributed operating system, you have essentially an OS that runs on multiple machines, and it hides the presence of multiple machines from the user. So the entire network of machines looks like one large logical machine. Okay? You log into something, but you don't know which machine you are logged into. Okay? You can submit a job to run. Okay? The OS is going to run it, but you don't know which machine it runs it on, because the whole thing just looks like a single machine. The fact that there are multiple machines comprising your system is hidden by the OS. Okay? As a transparency property that we were talking about. Okay? So there are distributed systems that will actually hide, okay, the presence of multiple machines. So to the user, it looks like a centralized machine. You just logged into a machine. Okay? It's a logical machine. There may be 10 machines as part of the network. The OS doesn't actually expose that to you. Okay? So you basically can get a high degree of transparency. It's much easier to use and whatnot. As opposed to saying, I want to log into the 5th machine of my cluster and submit a job. Okay? That system has not hidden the presence of multiple machines from it. Okay? That's not a distributed system. That's just a standard network operating system, which you are going to see next. Okay? So, yes, your question.
How is a single machine defined?
How is a single machine defined? Okay, we haven't defined a single machine, but a laptop is one machine. Okay, a server is one machine. A phone is a machine. So it's basically a processor, memory, disk, system bus. That's a machine.
Okay.
Okay. 2 processors on one machine, still one machine. 2 cores on a machine does not make it 2 machines. A machine can have more than 1 core, it can have lots of memory, it can have more than 1 disk, okay, but that is still one machine. Okay. Any other questions here? Okay. So we have distributed operating systems, but that's hard to pull off. Okay. Just as microkernels were a good idea that have some disadvantages, distributed operating systems are incredibly complex to build. Okay, you have to hide lots of things from the user, manage it on behalf of the user, and so on. So most operating systems don't actually go all the way. They use what is called a network operating system abstraction, which basically says that you are going to run a uniprocessor operating system, but it has networking capability. I can SSH onto another machine. I can essentially connect to other machines using applications like browsers. Okay? That's your standard operating system. Okay, Linux, Windows, Mac, they're all network operating systems because they're operating systems with good networking capability. Okay? They're not hiding the presence of other users, other machines. Okay? You still have to SSH to another machine and so on. Okay? But they give you some of the advantages we want when we build distributed applications, without having to complicate the operating system and make it fully distributed where it hides the presence of individual machines from the user and so on. Okay? So that's where most operating systems are today. Okay? They haven't taken that next step saying let's actually hide that presence and so on, although there are some systems that do that. Okay? There's one that's based on Linux called MOSIX. Okay? It essentially runs on a cluster, okay, and it makes the entire cluster look like one big logical Linux machine. Okay. So let's talk a little bit about multiprocessor operating systems, which was, I guess, the question you raised, or what is a machine. So you have uniprocessor operating system, which means that there's one processor and one core on that machine. Okay. Now most machines no longer have only one processor. Okay. Your phone actually has 8 cores probably. Okay. Your laptop may have 16 cores. So they have more than one processor or processing element. Shouldn't say processor. You may still have one processor with many cores, but there are many cores. Okay. So your operating system now has to essentially manage multiple cores. Okay. Essentially, you can decide which process runs on which cores. You can get true parallelism by running things simultaneously on multiple cores and so on. It is essentially an evolution from uniprocessor world. Okay. Multiprocessor operating system. Scheduling is harder. Okay. Synchronization is harder because when you have parallelism, you might actually have all kinds of problems if you are not synchronized and so on. Okay. So that's an evolution of a uniprocessor operating system. We won't say much about this in this class, but we'll get to one lecture where we'll have something to say about how do you do scheduling in a multiprocessor system. But that may be it as far as the course is concerned. Okay? And here is a picture, I should have put this earlier, of what a distributed operating system looks like. So here are your individual machines, A, B, C. Okay, they run their own OS kernel. There's a distributed service that runs on them. And everything about that runs above this essentially sees all these machines as single logical. Okay? So you take a sort of either a uniprocessor or a multiprocessor OS, you run a distributed system service on top of this, and you get a logical abstraction. Okay? As I was saying, this thing called MOSIX allows us to do exactly that. Okay? But it's not very this model is not that popular, okay, by and large. What you have is this network operating system model where you have multiple machines, you have your OS kernel, and then it provides networking services, so you can run TCP/IP application, you can run web browsers, you can log into other machines and so on. Okay, the presence of all these machines is now visible to this application. Okay? So you can actually see multiple machines access resources on them. So yes, question.
Yeah, on the previous slide, so the operating system is communicating with the kernel over the network itself. Right? The communication between the operating system and the three distributed kernels is over the network.
Yeah, so question is, in a distributed system, distributed operating system, are these kernels communicating with each other over the network? Yes. So this layer here, which is called distributed operating system service, is responsible for managing all the resources on multiple machines. So you'll have to communicate back because they have multiple machines. Okay? Yes.
Will this make it difficult to add a machine to the network?
Yes. So will this make it difficult to add a machine to the network? To some degree, you have to coordinate with that system service because you're extending the logical machine to include another. As opposed to a network operating system, you can just buy another Mac and put it on a network and you're done. Right? So I think it will be more complex than the network OS model. Yep. Okay, so this is where most operating systems are: Windows, Linux, Mac, OS. They all use this abstraction. Okay, network operating system. And as we showed, as I mentioned earlier, what this allows you to do is still build all kinds of interesting distributed applications. So this is a distributed file system where the client machine is accessing files stored on a server machine. I talked about cloud storage earlier, same concept. Okay? Just because it's this network, not distributed, doesn't prevent us from writing useful application. We can still do most of that work. Okay? So the last thing I want to say, then we'll wrap up, is you can take a network operating system model. Okay? You can write a software, you as a developer can write a software layer on top of this, which we'll call a middleware layer, and then provide similar abstraction to what distributed operating systems provide. You can then start hiding some of these services, not all of them, but some of these services, and let applications use all of the resources without actually having to figure out what runs where and so on. Okay? So now there are many middleware services that are not in the operating system. That's a software service that runs on each machine that provides similar abstractions to what distributed operating systems provided us. Okay? So you get some of that benefit back without having to make the operating system more complicated. Okay? And towards the end of the class, we'll talk about distributed middleware, okay? Which will allow us to do some of this. Okay, any questions? Yes, we have one last slide, which is just a comparison between multiprocessor operating system, multi-computer, which is a distributed operating system, network operating system, and middleware. I think the main thing is what is hidden, what is exposed, okay, how complex is it, and so on. I'm not going to go through this slide. You should go and look at it. But by and large, as you go from the left to the right, okay, there's higher degree of transparency. More and more things are hidden. Okay, and then, of course, complexity is also going to rise because more things have to be done by the OS as opposed to the user. Okay? So that's it for today. We'll stop here and then we'll resume next time. Okay?